In this video, we will be discussing about the coordinate system, the different types of coordinate system that we will be using in EE126. So problems can be simplified by choosing the right coordinate system. And in this section, we will be discussing these three: the rectangular, the first one; the second one, the cylindrical coordinate system; and the third one, the spherical coordinate system. They are the mostly used in electromagnetism. So for the rectangular, we have a bit of discussion about a rectangular from the previous discussions. So a coordinate in a rectangular coordinate system can be represented, the point can be represented by x, y, and z, where x is the distance from the y-axis, this one. It's the length of this side of this rectangular prism here. Then we have y, the distance from the x-axis. This is the x-axis. And z is the distance from xy plane, upward, positive z, downward, negative z. So if we try to plot, if we have we have a point in xyz or rectangular coordinate system. So if you're given, let's say, point P at 1, 2, and -3, then where is this point located? So first, 1 is x. So this is x, y, and z. So we can first locate x. X is the distance from the y-axis towards the x direction. So here, we can count 1. If this is 1, then that is our x. Then we go to the y direction with 2 units. So we go in this direction, 1 and 2. Then after that, we go in the z direction, because this is -3, so we go down by 3 units. So we go down by 3 units. So 1, 2, and 3. So therefore, this is that point P, 1, 2, -3. That's how we plot points in rectangular coordinate system. For the cylindrical coordinate, so it's important for us to know how to locate these points, because later on, when we are dealing with vectors or position vectors can be represented by the coordinates. So if you don't know how to plot them, then it's hard for us to visualize those vectors. So next, for the cylindrical coordinate system, the second one here. So if you're given, so the point can be represented again into 3 coordinates, or three parameters: rho, phi, and z. Where rho is the distance of the point. It's the vertical distance of the point to the z-axis. The z-axis, that's the distance, the shortest distance between the z-axis and that point. So if you look at this drawing here, it's the same distance as the length here, because that is just the radius of the cylinder. So if we continue to draw this, we can create a cylinder. It's just a quarter of a cylinder. So the radius of the cylinder is actually rho. And phi here is the angle coming from the x-axis. Coming from the x-axis towards that direction, or counterclockwise direction. It's an angle. It can be in radian, it can be in degree. Then for z is the same. This is still z. The distance of xy plane to the point is still z. The z in the rectangular coordinate system, it's the same as in the cylindrical coordinate system. Now let's plot. Let's try to plot something. Let's say 2, and we have phi angle, let's say 45 degrees. Then we have for the z, let's make it positive 3. So this is our rho. Rho is the distance from the radius of the cylinder. This is our phi, and this is our z. So first, we start at the origin. We count 2 units towards the x-axis or anywhere. So 1 and 2. Then what will we do next? We rotate this by 45 degrees. So we go in this direction until it's 45 degrees somewhere here. If that is 45 degrees already, then this is still 1 and 2. So we already rotate this one, rotated this one. 1 and 2. So this is now, and next will be, we go up, because it's positive, by how many units? By 3 units upward. So 1, 2, and 3. And this is now our point P. 2, 45 degrees, and 3 at the Z coordinate. So that's how we plot cylindrical coordinate system. And lastly, for the spherical coordinate system, the 3 coordinates this time is R. Now that R, to distinguish it with the radius at the cylindrical coordinate system, they are not the same R. They are not the same radius. Rho is the radius of the cylinder. R here in spherical, it's the radius of the sphere. So when we say radius of the sphere, we should start the distance from the surface outside the sphere to the center or the origin. That is R, and it's not the same as rho. Then we have still phi. The phi is still the angle coming from the x-axis here somewhere, and it rotates counterclockwise. Then another angle, this time is theta. This is a new coordinate. It will start at the positive z-axis, and it will go into this direction, clockwise direction. But remember, theta here, theta, the value for theta will be from, it can start at 0, start at the positive, can be 0 or greater than 0 until it has a limit, until pi, until at the negative z-axis. So that's the limit of theta, the value for theta. It will not go greater than that. And also, for the radius, we don't have any negative radius for the sphere that we have 0. It should be 0 and greater than 0. So our R will be can be 0 or greater than 0. Also for the rho in the cylindrical coordinate system, we will just treat the positive value for those magnitude, because later on when we derive the formulas, when I give you the formulas, you will know why it's always 0, positive or 0, from 0 to positive values. Now, how do we plot the coordinate in cylindric or in spherical coordinates? So if we do this again, so if we have, let's say, point P, we have a radius of 3. Then we have, for theta, let's say this is pi over 2. So pi over 2 is just 90 degrees. Or let's just make it less than 90 degrees. Pi over 4. Then we have, for phi, we have pi over 6 something. So this is our R, this is our theta, and this is our phi. So to plot this again, we have a 3 R, so 1, 2, 3. We rotate this one until we have this angle to be equal to pi over 4. Pi over 4 is somewhere around 45 degrees. So this is 45 degrees. And this is 1, 2, and 3. Then the next step will be, we need to rotate it an angle from here. So from the z-axis towards this point here. And that is pi over 6. Pi over 6 is 30 degrees. So if this is 30 degrees, this angle here is 30 degrees, or pi over 6. This is pi over 6. And if we project this downward, we connect it here, And we know this is also equal to 1, 2, and 3. So 3 units from the origin. And this will be our point P, which is 3 pi over 4 pi over 6. So that's how we plot coordinates into the 3 different coordinate system. Now, how do we convert coordinates from one form to the other form? So let's take a look at first when we are given with a rectangular coordinate system, rectangular coordinate to cylindrical. So how do we convert or transform cylindrical, a rectangular coordinate into a cylindrical coordinate? So we're given with a point x, y, and z. So we need to determine the values of this coordinate in terms of rho, phi, and z. So first, we need to solve for rho. What is rho? In terms of x and y. So if we look at this drawing here, let's try to redraw that in here. So if we join the rectangular and the cylindrical coordinates, so this is our rectangular. So we have our point somewhere at this point. So this is our point. Now, if we draw the cylindrical coordinate, so let's try another color. So for the cylindrical, it will go into that direction. And this will be the rho. So if we draw the top view, so that you can understand the concept behind this one, let's just draw the top view of this. So the top view is, this is the x and the y. So this is our rectangular, and this is our point P. So we know in rectangular coordinate system, if this is the y-axis and this is the x-axis, the distance from the x-axis is actually the y. So this is our y, and this one is our x. And I've drawn here that rho is actually the distance of that point to the origin, or the z-axis, not the origin. So this is our rho. So based from that, we can now solve for rho. So this is just a right triangle. If this is x, this is also x. So using the right triangle or the Pythagorean theorem, if we square that rho, the rho is just the hypotenuse of the triangle. So rho squared is equal to x squared plus y squared. So if we solve for rho, rho is just equal to the square root of x squared plus y squared. So if we look at this, there should be two values for rho. It can be negative or positive because it's square root. But we will only deal with the positive one because that's the distance. We take the rho to be always positive or 0. Next, for angle phi. So where is our angle phi here? So if we go back to the drawing again, this is our phi. The angle of this one is phi. Oh, so in our drawing, top view, this will also be equal to phi. And again, this is a right triangle. If you're given x, y, I want to solve for phi. What will be the formula? What will be the function using SOHCAHTOA? So opposite, y is the opposite side, and x is the adjacent side. So that's just tangent. So tangent of phi is just equal to the opposite side, which is y, divided by the adjacent side, which is x. So if we solve for phi, phi is just equal to tangent inverse of y over x. Then lastly, for z, the z is the same because z is a distance from the xy plane. In cylindrical and in rectangular is still z. So z is just equal to z. It's the same thing. So we don't need to convert that. So this is from rectangular. We're given x, y, z. We solve for rho, phi, and z. From rectangular to cylindrical. Now what if we change? We take the vice versa. We are given with the cylindrical and we want to solve for the rectangular coordinates. So from cylindrical to rectangular. So how do we do this? Let's use again this triangle here. That triangle will be the basic relationship between the two. So this is 90 degrees right triangle. This is our phi. This is our rho. This is x and this is y. From here. And we will base it from that. So this time, we want to solve for x, y, and z. We're given with the cylindrical coordinates rho, phi, and z. So we want to solve x, y, and z. So what will be x? So we base it again on the drawing under the right triangle. So if I solve for x, given rho and phi, so what will be the function that relates x, rho, and phi? So phi is the angle, rho is the hypotenuse. So if we go back again to SOHCAHTOA, so TOA. So what function that relates the adjacent side and the hypotenuse side? So it should be cosine. So if we take the cosine of that angle phi, cosine phi, that should be equal to the adjacent divided by the hypotenuse. The adjacent side is just x divided by rho. So I want to solve for x, then x will be equal to rho times cosine phi. So this will be our x in terms of rho and phi. For y, it's the opposite and the hypotenuse, so it should be sine. So sine phi will be equal to y all over rho, opposite over hypotenuse. So y is just equal to rho sine phi. And for z, again, it's the same. Z and z are equal. So this is how we convert from cylindrical coordinates to the rectangular coordinate system. Now, let's go to rectangular and spherical. So from rectangular to spherical coordinates. So let us first look for that one. So we're given with x, y, z, this coordinate, and we want to transform this into spherical coordinates, which is r, theta, and phi. R, theta, and phi. So again, we need to relate the drawing, just like what we did here in the rectangular and cylindrical. So we need to combine these two and look at what is the relationship between those lengths and sides and angles. Let's try to copy this in the figure here. So this is in cylindrical. Now let's draw in spherical, let's draw the rectangular part. So let's say so if this is the rectangular, that's going downward here. That is our point. Now from that, we can label this is our y here, this is our x, and this is our z values. So first, we need to relate them. So we can, if you look at this, the r here is actually the diagonal of the rectangular prism in this drawing. So first, if we want to solve for that r in terms of x, y, and z, this is also y here, this is x here. First, we can solve for the length at this side from here to this point here. And that is just equal, this length is just equal to the square root of x squared plus y squared. Then this is 90 degrees. This is z. This length here is z. And if we draw that triangle, this is that x squared plus y squared, the square root. And this is right. This is the origin. This is the point of origin. This is our point P. And this is our R. We know that this is Z. And we also know that this side is equal to the square root of x squared plus y squared. Why? Because if we draw the triangle, that side is just the hypotenuse of this right triangle here. This is also 90 degrees. And this side is equal to square root of x squared plus y squared. If we try to draw that, this is the origin again, and this is x, and this is y, this is 90 degrees, and this side is equal to that side, square root of x squared plus y squared. And we include it here so that we can solve for r. So we can apply again the Pythagorean theorem. We square this one, we add it with the square of this one, then we have the square of the hypotenuse r. So r squared is just equal to z squared plus this side, which is the square root of x squared plus y squared. You square it, and that will be x squared plus y squared only. The square root will cancel out. So if you solve for r now will be just equal to the square root of x squared plus y squared and plus z squared. So this is the formula for the radius of the sphere. Now, next, for theta. Where is theta? Our theta is this angle somewhere here. That is theta. So if we draw again a line from this point to this point, so this side again is the square root, it's still this one, the square root of x squared plus y squared. It's just the upper version of that in the bottom, but they are the same length. Then r here, then we have also z here. So if we redraw that again, that triangle, we draw that triangle. This is our z. This is the origin point of origin, and this is that square root of x squared plus y squared. And the end of that is that point, our point P. And if we connect the origin and that point, that is just our rock. And where is that angle theta? This is the angle theta here. That's the angle from the z-axis. So if we want to solve for theta, but remember rho here is not given. We already solved, or this is not rho, this is r. This should be r. R here is not given, so we don't need to include that in our formula. We can just remove that. But x, y, z are given. So the opposite side and the hypotenuse, or the adjacent side, are given. So what should be the function that relates these two? So it's opposite and adjacent, that should be tangent. So tangent of theta is equal to, this is right triangle, the opposite side, which is the square root of x squared plus y squared all over z. And if we solve for theta, theta now will be equal to tangent inverse of that, the square root of x squared plus y squared all over z. So this can be a form. This is one of the formula actually. We can also use this side because we know that this is r, but r is not given, but we know that r is x squared plus y squared plus z squared. So we can also use that one. And we can use any function actually. We can use cosine. So if we use cosine theta will be equal to the adjacent side, which is z, divided by the hypotenuse, which is that r, or the square root of x squared plus y squared plus z squared. And z, x, y, z, these are all given. So we can solve for theta. Theta is just equal to the arc sine or cosine inverse of that, z over the square root of x squared plus y squared plus z squared. We can also use sine if you want, sine theta. Sine theta is equal to the opposite side, which is square root of that, square root of x squared plus y squared all over the adjacent, or the hypotenuse, which is x squared plus y squared plus z squared. And if you take the theta, take the sine inverse of that side, this will be equal to the square root of x squared plus y squared all over x squared plus y squared plus z squared. So they're all the same. They're all equal to theta. But it's up to you what formula are you using. You can use this one. You can also use this cosine inverse here. This is what is in mostly in the book. I've seen in the book they use this one, cosine inverse of z. over the square root of x squared plus y squared plus z squared. But remember, you can use any of this formula, but remember that theta should always be from 0 to pi only. Pi only. You cannot go higher than pi. Okay, so this is how we convert. Or next, we have also for z or phi. How about phi? How do we solve for phi? So where is phi in this drawing? This is our phi. So you can just draw the triangle here. The triangle. This is x, right triangle with y. So if we draw that again, we have a right triangle. So this is a right triangle. This is x. This is phi. And this is y. And this is the square root of x squared plus y squared. So you can use again any of the functions. But the more simpler one should be the opposite over the hypotenuse. Or the opposite over the adjacent side, because it's just y and x. There's no square root in the formula. So we can just use that. So phi will be equal to tangent inverse of y over x. It's the same formula as we have in the cylindrical coordinate system. So it's better to use this one either than the other formula. So this is from rectangular to spherical. Now we do the vice versa, from spherical to rectangular coordinates. So this time we are given with r, theta, and phi. And we want to transform this into x, y, and z. We need to solve for x, we need to solve for y, and we need to solve for z. We need to draw again the figure so that we can relate these two coordinates. So again, we have our rectangular prism somewhere here. Now this time, we are given r here. We are given theta. This is theta, and this is phi. And we want to calculate or solve for x, y, z. So where's x? Our x is this length here, and our y is this length, and z is this length, that distance. So in order to do that, we use geometry and trigonometric identities, some trigonometric identities. So first, we can solve for x. So we draw this triangle again. This is 90 degrees, a right triangle. So if we draw that, so this is our x. This is the origin. And this is angle phi. So to solve for x, we cannot use the value for the side that is equal to the square root of x squared plus y squared, x squared plus y squared anymore, because x and y are not given. So we need to solve this side in terms of r, theta, and phi. And to do that, we need another triangle. This triangle, the other triangle here, is one from here, here, and to here. And this side is actually this side here. So if we draw that triangle, this is r, and this is this side. And we know that this angle from, if this is the z axis, this is our theta. And if that is theta, this is also equal to theta. And if this is now theta, we can apply some trigo to solve for this side. What will be this side? This will be equal to the opposite and the hypotenuse. So opposite and hypotenuse is sine. Sine theta is equal to this side divided by r. So if we solve this side, this is just r times sine theta. And this will be our side here. This is also r sine theta. Now that we know this side in terms of r and theta, not in x, y, z, then we can use that to solve for x. So to solve for x, again, we use SOHCAHTOA. So x is the adjacent side of the the angle phi. So if it's adjacent, so we use cosine, ka. Cosine phi is equal to the adjacent side, which is x, divided by the hypotenuse. Our hypotenuse now is r sine theta. So if we solve for x is just equal to r sine theta times cosine phi. This will be our x, converted from spherical coordinates to cylindrical coordinate. How about for y? So if it's y, it's the same thing. Instead of x, we use this y here. This is y. And it's just the opposite. So instead of cosine, we use sine. Sine of phi is equal to the opposite side, which is y, divided by the hypotenuse, which is r sine theta. And solving for y will be r sine theta multiplied by sine phi. And lastly, for our z is this side here. This is our z. This is the length. This is the point, P. And this is the origin. So this is z, the distance from the xy plane towards the point. So if we solve using this triangle, given r and theta, we can solve for z. So hypotenuse, r, and z is the adjacent side. So that will be just equal to cosine. The cosine of theta will be equal to the adjacent side, which is z, all over the hypotenuse, which is r. So z, therefore, is equal to r times cosine of theta. So these are our formula. Given spherical coordinates, we converted them into rectangular in x, y, and z. And for the last conversion, so we did from rectangular to spherical, spherical to rectangular. We did rectangular to cylindrical, and cylindrical to rectangular. How about from cylindrical to spherical? So this will be our last conversion, cylindrical to spherical and vice versa. Spherical coordinate. So we're given with rho, phi, and z. And we want to solve for the spherical coordinates, which are r, theta, and phi. So we need again this drawing, but this time instead of rectangular, we draw a cylindrical here. So this is our point. Just another color. So this is not rectangular, it should be a cylinder. It looks like a rectangle. Let's try to draw it again. Oh, come on. So imagine it's a cylinder. It's a cylinder. Just imagine that this is a cylinder. And the distance from this point to this point is r, or rho, our rho. And this is rho. And this is still phi. And we want to solve for r, theta, and phi. So the phi is the same phi as the phi in the cylindrical coordinates. They are the same. So we can just use that later on if we want to solve for phi. So first we solve for r, this is r, and then we can solve for theta here. So for r, so if we have a triangle, we can use this triangle here. From here, this point to that, and that. By the way, this side here, from the origin toward this point, this is z in cylindrical coordinates. So if we draw that, here, we isolate that triangle. This is z, this is 90 degrees, and this is our rho, and this is r, and this is theta. And this will be the relationship now. So to solve for r, in terms of rho and z, remember, rho and z are given. This is in cylindrical coordinates. and we want to determine r, so we can just use Pythagorean theorem. R is just the hypotenuse of this triangle, while z and rho are the sides of that triangle. So r is just equal to the square root of the sum of the square of the other sides, which are z squared and rho squared. Or we can just interchange. This should be rho squared plus z squared. Rho here, this is the radius in cylindrical. So that's the formula for r. Now, next is for theta. So again, we use this triangle, given rho, given z. So if we solve for theta, what will be theta? Opposite and adjacent side. It should be the opposite and adjacent side. So that will be tangent. Tangent of theta will be equal to the opposite, rho, over the adjacent z. So theta is tangent inverse of rho over z. And again, we can use this r here because we know that r is rho squared plus z squared, and rho and z are given. So instead of tangent, we can also use cosine. Cosine theta is equal to the adjacent side, which is z, divided by the hypotenuse r, which is equal to the square root of rho squared plus z squared. So theta can also be written as cosine inverse of z all over the square root of rho squared plus z squared. So we can use those formulas to solve for theta. And for phi, again, that's the same. Phi is just equal to phi on the cylindrical. Because this is also the phi in cylindrical coordinate, and this is also the phi in a spherical coordinate system. So this is how we convert from cylindrical to spherical. If we do the vice versa from spherical to cylindrical system. So we're given with r, theta, and phi. We want to solve for rho, phi, and z. So using this drawing again, this triangle here, we can relate the two coordinates, z, theta. Now, we're given with r, theta. So r and theta are given. If I want to solve for rho, given theta and r, it should be opposite and hypotenuse. Opposite and hypotenuse, that is sine. So sine of theta is equal to the opposite side, which is rho, all over the hypotenuse, which is r. But don't use r, the square root of rho squared plus z squared, because that is not given. What is given is r. Then solve for rho. Rho will be equal to r sine of theta. Next, for phi, solving for phi, again, they're the same. Phi is equal to phi. If you do the vice versa, it's also the same. For z, let's go back to this triangle again. Z is the adjacent side, and r is the hypotenuse. So adjacent and hypotenuse, AH, that should be cosine. So cosine of theta is equal to the adjacent side, which is z, divided by the hypotenuse, which is r. So this is z all over r. So solving for z is equal to r cosine of theta. And this is how we convert coordinates into the different coordinate system. So we can convert whether you want from rectangular to spherical and vice versa, or any of those coordinate system.